Can you see the slides?
Yes, perfect.
So hi, I'm Ramil, and today I'm going to talk about our work on using BERT for sequence-to-sequence multi-label classification. I'm currently a PhD student in Higher School of Economics, and this work was done in collaboration with Pavel Serdyukov as a part of our research work in Yandex Taxi. Just to remind, multi-label classification is the task of learning a function that maps text samples to multiple labels from a label set. So initially we have a data set of pairs and also given label sets. And yeah, for example, what's the difference between multi-class and multi-label classification is that in multi-class we only assign one label per sample, and in multi-label classification we can assign many. And in this slide, I also illustrated how the usual pipeline of a classification model looks like. So we have a text, and then there is some base model that does some representation learning and outputs a fixed size representation vector. And after that, a classification algorithm, for example, in deep learning, it may be just a dense layer. It inputs this fixed size representation vector and transforms it into a probability distribution over the set of labels. So this is a usual pipeline, and in a particular case, when the number of classes is large, it also can be useful to have some prior knowledge about the classes in the form of a hierarchical structure. And here is the example of a tree hierarchy over the classes from a data set on ticket tagging in taxi client support system. So for example, if we had a text sample, I waited for the driver so long from an angry customer, let's say, we can say that it would belong to the driver was late category, and also to all the categories in the path between the root node and the leaf node. So yeah, this kind of hierarchical structure, it may help us to classify underrepresented labels in our data set, and this is one of the key points why we might want to use this hierarchical structure. One of the promising methods to tackle this problem of multi-label text classification is using sec-to-sec modeling. In this approach, a model predicts labels in a sequential way, taking into account previously predicted labels. In this chain rule decomposition of the joint probability of a set of labels given an input X, there are two primary ways to order the labels. So we can see here that like with any order, this decomposition would be true, but to actually model this sequence, we basically have two approaches because we don't actually. So in this task, we don't have a natural ordering in the output sequence as we would have in machine translation, for example. So we have to order the labels somehow, and one approach is to order the labels by frequency of labels. And if we are presented with a hierarchical tree, we can also use topological sorting. And with this obtained order on L, so this problem can be viewed as a sequence-to-sequence task. And yeah, this idea was first introduced by Nem in 2017, and it's quite nice. I think it's like kind of novel and interesting approach to this problem. We argue that in this sec-to-sec setting, we we can use a heavy language representation model such as BERT as an encoder. And in our implementation, we passed the BERT representation of CLS token into an LSTM decoder. So, and we use we use representations of other tokens in the BERT for attention mechanism. And also in each step we perform here a mask softmax instead of just softmax to avoid repetition of the labels. And for example, in the case when we are presented with hierarchical structure, we also want to avoid the labels that are not in our path. So if we already predicted some labels previously and we want to predict a new one, we should probably mask out those labels that were already predicted and those that we don't want to predict because they are not in the possible path between the root and any leaf node. Just one more thing. We train this model using the cross entropy objective and ground truth labels. And in the inference stage, we can compute the objective, replacing ground truth labels with the predicted labels. So it's a basic teacher forcing technique, and we use it in our implementation as well. In the experiments, we have 5 data sets. So 3 of them are popular English data sets, and the other 2 are private Russian data sets from Yandex Taxi support system. And one of the baselines that we considered is just a straightforward vanilla BERT for multi-label classification. And yeah, we followed the same implementation details as in the paper doc-BERT. So we trained the model using the binary cross entropy loss, and yeah, that was one of the baselines that we used. Our error analysis has also shown that often multi-label BERT can predict excess labels, and while sequence generating BERT tends to be more restrained, and this suggests that the 2 approaches can they may combine each other well, so they may complement each other well. And in the sec-to-sec setup, so it's more difficult to produce a probability distribution over the classes, obviously, and we tackle this problem as per the paper of Salvador from CVPR 2019, and we basically use max pooling operation over the probability distribution that were produced in the decoding stage. So in the decoding stage, in each stage, we had this probability distribution after performing masked softmax iteration, and we just max pool them. So we take the maximum over each coordinate in the over all the probability distributions from the decoding. So at the end, we form the mixed probability distribution by combining those 2 distributions. So it's just a weighted average with alpha being a trade-off parameter optimized on development set. Yeah, here is the example how how it behaves in a development set of RCV1 dataset. So we can see that it prefers so for two metrics, at least accuracy and micro F1, it prefers just a vanilla BERT as a major contributor to the probability distribution. And as regards to macro F1, we can see that so the larger weight, so BERT sequence to sequence BERT has larger weight in this case. Yeah, and just regarding the evaluation metrics, so we compute here a micro averaged F1 and macro averaged F1, and the difference is that micro averaged F1 it's sort of biased towards the more frequent labels, and macro averaged F1 it treats the labels as equally important. And for example, if we want to measure the quality of the model on more underrepresented labels, then we should probably look at macro average F1. Otherwise, so micro F1 is a good metrics. Yeah, the experiment results are presented in the table. In some cases, BERT performs better than the sequence-to-sequence version, which is especially evident in the Reuters dataset. And the possible reason for that might be that this dataset is the smallest one out of the 5 dataset we had. And however, for example, in RCV1 dataset, which is quite large, we can see that BERT sec-to-sec is has much better macro F1 metrics. For both Yandex Taxi datasets in Russian language, we also can see that the accuracy of the sequence-to-sequence BERT model is higher compared to other models. In most cases, better performance can be achieved after mixing BERT and sequence-to-sequence BERT, and so we haven't seen like large improvement in micro F1 metrics, but for macro F1 metrics, it's about 1.6 average improvement, and as regards to accuracy, it's about 0.8% improvement. And so in this table, we also so the matrix is marked as bold if it's significantly so statistically significant. So if there is a statistically significant difference with other metrics in the same category. So also we also observed that BERT-based models, we also observed that BERT-based models show more favorable results in comparison to other models. We also, for example, took 2 baselines, HMCN and HILAP, from 2019 conferences. So HMCN was presented in ICML conference, and HILAP was presented in YAMNLP conference. And those 2 models so underperform compared to BERT-based models. And this is also yeah, interesting. So we also can see that multi-label BERT takes 30 to 50 epochs to converge, and this is actually unexpected, because in multi-class BERT, for example, it really takes smaller few number of epochs to converge for the BERT model. However, in multi-label case, and this was confirmed in the previous paper about that, it's true that BERT multi-label takes like several dozens epochs to converge. So in comparison, our model BERT with sequence to sequence, with sequence generation model, it really achieves decent accuracy much faster, and converges just after 8 to 12 epochs, and even before that. So it requires less than 1 epoch. So basically, less than a whole data set to show really good accuracy. And also in this slide, we show how differently the BERT sequence to sequence and the usual vanilla BERT perceive the same text. Well, it's so in some tokens, it's quite obvious that so for example, for the words encoder and deep, in both models, it pays large attention to it. But for some other words and tokens, we can see that the distribution of this attention is different. Yeah. And just to sum up, the results are that this BERT plus SGM model with sequence to sequence setting combined with a standard BERT, it outperforms the baselines on 3 popular datasets, and so BERT for multi-label tasks, it takes far more epochs to converge, and sequence to sequence BERT in comparison achieves decent accuracy much faster. And also one of the findings was that the beam size, so we performed beam search in the inference stage, and it appears that beam size does not affect much on the performance. So it's an interesting finding, because it actually matches sort of to the intuition, because for example, in machine translation, we do have this problem with ordering. So in beam search, the model can produce different sentences, for example, and they might be in machine translation, they might be equally good translation of the source sentence, but in our case, the order is quite unimportant, and yeah, this might be one of the reasons, and another reason might be that the vocabulary size of in our task is much smaller, because we only have the classes. So our vocabulary is basically the labels in the data set, and in machine translation, they are so the vocabulary is the words. Yeah, and just a small slide here with ideas for future work. I I think one of the interesting lines of work would be learning a this hidden hierarchical structure over the label space where no such hierarchy is presented. Another interesting problem is to attempting to generalize this idea to large scale multi-label classification, because in this case we would have even larger sequences, output sequences, and maybe the pros of sequence-to-sequence BERT model would be more apparent and evident in this case. Also, if we can go further with adopting this sequence-to-sequence ideas from other natural language sequence generation tasks, such as machine translation, summarization, for example. And in these fields, there were many interesting ideas proposed already, such as deliberation networks, and using, for example, pure transformers as a decoder model. Yeah, these techniques, it would be interesting to see how they work in this multi-label classification, text classification problem setting. So thank you very much for the attention. I'm ready to answer the questions.
Thanks, Ramil. We already have actually 3 questions in the chat. So it would be nice if you can. Yeah, they're both from they're all from one and the same person. Mikhail Tikhamirov asks about trying your approach for Russian datasets, about multiple different seed values, and why do you think it's so many for convergence?
Yeah. So so the first question is, did you try RuBERT for the Russian datasets? And the answer, so my answer for that is yes. Yeah, we tried this for just a vanilla BERT model. We didn't try it for sequence-to-sequence BERT, but for the standard BERT model, it actually didn't in our task. So in Yandex Taxi dataset, Russian dataset, it didn't affect much on the performance. We actually even tried conversational BERT, which probably should have been even more appropriate than maybe RuBERT in this setting, because in Yandex Taxi dataset, the language of the text is quite informal, yeah, and but neither RuBERT nor conversational BERT did not really improve the results. Yeah, and should I continue to answer the second question, or
yeah, sure.
Yeah, so so about multiple experience with different seed values. No, we did not try. So we did not try it like we did not run this experiment like very thoroughly and did not report such results. However, surely in the process we run the program several times with no fixed seed, with no fixed random seed, and the results were pretty persistent and robust. I mean, they were different from time to time, but they were quite close to those numbers that we reported in the paper. And regarding the third question, why do you think it took so many epochs for convergence? So in multi-label classification, I don't have a good answer for that. So I only know this from the experimental side. So we performed these experiments, and indeed, after, for example, like 3-4 epochs that should be enough, for example, in multi-class classification, it's absolutely not enough in multi-label classification task. And yeah, these results the same results were actually obtained in this paper, BERT by Hikari. In this paper, they also report that the number of epochs it took to converge was much larger. So yeah.
Okay.
Thank you.
Thanks, Ramil. We have to move on to the next talk. But if
thank you very much.
If anyone still has questions for Ramil, please ask in the Zoom chat or in our Telegram chat.
Yes, I would be more than happy to answer the questions. Yeah, thank you.